됐어요? 자, 20분 되면 신호 좀 주세요. 네. 자, 소리도 나와요? 소리?
예, 나와요.
네. 자, today I want to present regarding the analytical study of back pressure according to the porosity and the numerical change of DPF filter. This is based on the DPF study. So we have to understand the structure of the DPF. So I want to study about the back pressure and then temperature variance. Today I present in this way, first introduction and second experiment, third results, and finally I make some conclusions based on the previous results. For the introduction, I wrote in this page that these engine have used the after treatment device to cope with the stringent environmental emission regulations. These are particulate filter that reduce the PM is composed of porous filter. And as the mileage accumulate, soot and ash accumulate inside the filter, and the back pressure increase. In diesel particulate filter, periodic regeneration is necessary to remove PM, which is particulate matter, and the porosity of DPF is the major variables that determine the regeneration cycle according to the filter efficiency as well as the back pressure characteristics. Therefore, in this stage, we investigate how we change the DPF porosity, geometric size, and the change in the particle diameter passing through the filter affect the back pressure and temperature of DPF. In this side, the temperature of DPF is very important, and back pressure is important because we need to remove the accumulated PM inside of the DPF. For the investigation, I used the computational fluid dynamics analytical solutions can significantly reduce time and the cost required for the internal flow analysis. So, CFD technique was used to analyze the porosity and back pressure characteristics of DPF according to the cross-sectional diameter and the particle diameter. In addition to this, in this study, is as a follow-up study, the characteristics of back pressure and the temperature distribution according to the correlation between the change in porosity and structure shape of filter are made of porous material or study. In general, the higher porosity of DPF filter, the more advantages of PM filtration capacity is. So the industry tend to prefer filters with higher porosity. However, since filtration capacity and back pressure and temperature distribution and the characteristics are in the trade-off relationship, this research was conducted to develop DPF having an excellent back pressure characteristics with optimal DPF filtration capacity. For the diesel particulate filter, which is called the DPF, is a device that collects and burns PM inside the DPF. There is a porous stacked structure called cake layer. On each floor, ceramic plug ultimately block of both sides of passages, and it just gets entering often passages through a perforate hole in the ceramic wall and filters PM. Since the accumulation of such dust impairs filter permeability and result in the pressure drop. And the filters has been developed to minimize ash accumulation. For example, the filter structure with asymmetrical channels have been studies to remove honeycomb-shaped channel structures. The result of CFD study shows that when the accumulation of dust is high, the pressure drop can be reduced by designing different inlet and exhaust channel width. In this research can extend regeneration cycle of DPF. Therefore, this study applied numerical analysis technique based on the finite volume method and assumed compressible turbulent flow in normal state of for exhaust flow. Accordingly, the compressible flow based on momentum equation and the continuous equation and the turbulence motion equation was applied together. To solve the equation, the RNG K0 turbulence models were applied, which calculate relatively robust results for flow for turbulent flow was used. High porosity DPF filter was set as a porous medium, and the internal flow was assumed to be a laminate. Shows the standard shape and the mesh model of DPF used in this study. And also, we have to understand the diameter. Is the diameter of the exhaust pipe connected to the front and rear end of the DPF was fixed to 80 millimeter. And the diameter of length of DPF substrate was changed, according to in accordance with the analysis conditions. Mesh element was composed of total 100,000. The mesh element size of DPF substrate is 0.001 millimeter. This is a show I described DPF, and inlet this is 8 millimeter, and then outside is sometimes we have to change this size, inlet, outlet, and so there are many variants were involved. So we have to understand clearly. And also, there inside the DPF, we have unstructured, we apply unstructured grid generations and so that. So we have to understand this kind of pitch curve phenomenon flowing inside from the engine, and then there is some accumulate for DPF, and then we out like this. So that's very understand this kind of structurally understand the DPF. So this is basic geometry of the DPF. We try to study this. This is kind of a table for feature system and DPF models and specifications. The index mass flow rate is we apply for this flow mass flow rate, and the outlet temperature is 1 atm. This is atmosphere temperature. Injust temperature is this 576 Kelvin degree, and the porosity is we have different porosity applied. In this case, is 45, and the percentage is 76, 55, and then there is 15 percentage differences. And for the TPF model, the diameter of particles is also we have to we apply different diameter of particles like this, and we have 4 different particles. And the specification for this specification, diameter of the substrate are like this, okay, and the length of substrate are like this. Okay. This is kind of this is the test line schematics of standard DPF system with the vortex flow. Obviously, we can see they're inside, and then there's an inlet. There's some flow inside, and then suddenly the diameter is narrow, and then wide instead. So that's why there is lots more voices were formed in this way, like this. Okay. And then they go inside and outside like this, and then this is more obviously pictures we can understand like this. Okay. There is inside and outside, and then there's clear difference in there. And to understand the pressure gradient characteristics according to the change of porosity and cross-sectional area, the porosity will change to 45% and the 60% and the 75% and the 90%, and the pressure drop before and after DPF. For there, 3 types of cross-sectional area were analyzed. So we can just I mentioned about this one. So this kind of we have like this, and there is some differences. So we apply the x-axis represent porosity, and then there is different different porosity we apply in this case, and the pressure drop. Y-axis pressure drops. Okay, and here is different diameter we applied in these cases. Okay, so obviously the pressure, porosity is much bigger, and the pressure is going to be decreased. This is very clear evidence we can understand. Okay, the porosity is more bigger. The size of the shell is much more bigger, and then pressure drop is low. Okay, this is this, but and also we have to understand the diameter like this. Okay, this is the more smaller one than this. Okay, so smaller one is a pressure drop like this way, but the overall the condition is almost the same like this. Okay, like this, and then this, but this is much more big. Pressure drop is much more bigger because okay. So okay. So I guess it's enough to understand from these figures. This figure shows the pressure control for DPF with the 300 milli length. Okay. And first one is A is 45% of porosity, and the B is 60% of porosity, and the 75 is 90% of porosity. So we see inside of the DPF is not clear, but look at in this way, like this. Okay. And the outside temperature, this is outside. This is not temperature. This is pressure. Right? Pressure is much lower than this. Okay. Okay. Because porosity is increased in this way. This is much more. This is 90% porosity. This is 75% porosity. This is 60, and then this is 45%. So obviously this is much more porosity increase. So pressure drop is easily. So we have to understand the kind of how come develop the pressure gradient inside of the DPF. This is the according to the previous station arrow in this way. That's the pressure, and then front and the rear pressure and drop. So front is 65 for this case is length is 20. Okay, is the millibar, and the 5.9 is the 18.4. And then this is we increased the length up to 250 millimeters, and then a little bit increased. Okay, a little bit increased the pressure. Yes, look at this one and this one. Okay. But for this one, these two cases, front, right? But anyway, inside the pressure, when for inside of DPF, the front section is 24, but pressure drop this much. Okay. This one increased, okay, but this one is much more bigger one, okay, bigger one. Bigger one, so it's 5.2, and then last the boundary. And also, I have to show some kind of temperature control called TPF, like this. And then A is the 8 millimeter, B is 6 millimeter, and then the C is 4 millimeter, and then 2 millimeter. There is some temperature differences in there. Okay. Obviously, this one is much more. This is lower, lower temperature, but this is much more higher temperature showed. I make some conclusions in this study. CFD analysis was performed to investigate back pressure characteristics according to the change in the porosity, geometric size, and particular diameter of TPF, and the result follows in this way. As the cross-sectional area of TPF increased, back pressure decreased. In addition, if the porosity is increased TPF with the same cross-sectional area, the back pressure is decreased. But if the porosity is increased by 75% and more, the average flow speed decreased and the back pressure is increased again. And then increase the length of TPF in this friction pressure on the wall surface, thereby increasing back pressure. However, rather than increase of the back pressure with the length, decreasing the length, back pressure with the increase in porosity is greater. The lower porosity and the smaller particular diameter, the larger back pressure, and the temperature gradient occurred. As the porosity increased, the back pressure decreased. But under the porosity condition of 75% or more, the back pressure converged to one uniform value under all particular diameter conditions. 어떻게? 저장.